Welcome to the last lecture of MECH 6520, Manufacturing of Polymeric Structures. Today's lecture will focus on extrusion in food manufacturing, specifically on the process principles, equipment design, operating parameters, and product applications. My name is Parker Hasty, and I'll be your substitute lecturer for this class. Even though this course primarily focuses on manufacturing of polymeric structures, extrusion is also a major process in food manufacturing. Many of the same engineering ideas still apply, including material transport, heat transfer, screw design, pressure buildup, and die shaping. So today I'll walk you through how extrusion works in food systems, the main components involved, the variables that control product quality, and how the process is used across modern food production. Food extrusion is a continuous thermal-mechanical processing method that involves mixing and compressing food materials at elevated temperatures before forcing them through a die. In simple terms, ingredients are fed in a machine, processed under heat and pressure, and then shaped into a final product as they exit. This process is commonly used for starch and protein-based materials. Some of the most familiar examples are snack foods, breakfast cereals, pet food, and pasta. Because extrusion can handle many different formulations and product types, it has become one of the most widely used processing methods in the food industry. Another important point is that the final product structure and texture are strongly influenced by the processing conditions such as temperature, pressure, moisture content, and shear. So extrusion is not just a shaping method. It is also a transformation process that changes the internal structure of the food. Overall, food extrusion is valid because it offers high production efficiency, a lot of product versatility, and relatively low operating costs compared to performing these steps separately. Inside the extruder, the material experiences several different actions at the same time. It is being mixed, compressed, sheared, and heated as it moves forward. These combined effects cook the material and also modify important food components like starches and proteins. That is one reason extrusion can produce such a wide range of textures and structures. The heat inside the system comes from two main sources. One source is external barrel heating, and the other is mechanical energy generated by the rotation of the screw or screws. At the same time, pressure continues to build as the material gets closer to the die. When the product exits the die, the pressure drops suddenly. That drop can cause moisture to flash off into steam, which creates expansion. This gives what many extruded foods, like puff snacks and cereals, their porous and crisp texture. So when we think about extrusion fundamentally, it really is the interaction of moisture, heat, pressure, shear, and die discharge that determines the final food product. A food extruder includes several key machine components that work together as one processing system. The process begins at the feed hopper and feeder. Their job is to introduce raw ingredients into the machine at a controlled and consistent rate. That is important because unstable feeding can affect pressure, residence time, and product quality downstream. The core of the machine is the screw and barrel system. The screw, or in some systems, multiple screws, rotates inside the barrel and performs multiple functions at once. It conveys the material forward, compresses it, mixes it, and thermochemically processes it as it travels through the machine. The barrel itself often has temperature control zones, so heat can be applied and regulated along the length of the process. Some systems include injection ports, which allow water, steam, oils, or other ingredients to be added during operation to improve control and consistency. At the discharge end, the die shapes the product into its final cross-sectional form. After that, a cutter is often used to control the final product length and improve uniformity. So while an extruder may look simple from the outside, it's actually a highly integrated processing system, and most of these systems are more complex than what we've seen in class. Now we're going to talk about polymer extrusion versus food extrusion. Food extruders are designed for sanitary, corrosion-resistant operation, especially on product contact surfaces. Because of that, materials like 304 and 316 stainless steel are commonly used. In food systems, material selection is heavily driven by food safety, cleanability, and resistance to cleaning chemicals, not just strength or wear resistance. Polymer extruders, on the other hand, are designed around a different set of priorities. Their barrel and screw systems need to handle high pressure, abrasive fillers, elevated temperature polymer melts, and long operating life under harsh mechanical conditions. Because of that, polymer extruders are often made with nitrided steels, hardened alloy steels, or tool steels. So the main distinction is food extrusion prioritizes sanitation or corrosion resistance, while polymer extrusion prioritizes wear resistance, thermal durability, and service life under abrasive processing conditions. Even though the applications are different, it is interesting that both food and polymer extrusion still rely on the same broad engineering ideas of conveying, pressure development, controlled heating, and die shaping. One of the most important parts of food extrusion is controlling the process variables. These variables have a major effect on product quality and consistency. The first major variable is feed moisture content. Moisture strongly affects viscosity, expansion behavior, density, and specific mechanical energy during extrusion. Lower moisture often leads to greater expansion and higher mechanical shear, while higher moisture generally reduces viscosity and lowers energy input. The next major variable is barrel temperature, which influences cooking intensity, starch gelatinization, protein denaturation, and final product temperature. Higher temperatures can promote expansion and desirable structural changes, but if the temperature becomes excessive, it can negatively affect color, temperature, or nutrient quality. Screw speed is another major variable. It changes shear rate, residence time, mixing behavior, and throughput. In many cases, increasing screw speed improves mixing and texturization, but the exact effect depends on the formulation and the other operating conditions. Feed rate is also critical because it affects how full the extruder is, how pressure develops, and how stable the process remains over time. Finally, die geometry and die temperature help control pressure drop at discharge, the product shape, the degree of expansion, and the final texture. So overall, extrusion quality is highly dependent on process control. Small changes in one variable can significantly affect the final product. Food extrusion has a broad range of applications across the food industry. One of the most common applications is the production of expanded snack foods and ready-to-eat breakfast cereals. In these products, the rapid pressure drop at the die creates porous, crisp structures that are characteristic of puffed foods. Extrusion is also widely used for pasta and noodle production. In this case, the process provides controlled shaping, dimensional uniformity, and continuous high throughput manufacturing. In high moisture systems, extrusion can also be used to produce texturized vegetable proteins and meat analogs. In those applications, the goal is not just shaping, but also restructuring plant proteins into fibrous meat-like textures. Food extrusion is also very important in pet food and animal feed manufacturing. That is because the extruder can combine mixing, cooking, shaping, and partial sterilization into one operation, which makes the process both efficient and practical at industrial scale. More recently, extrusion has expanded into functional foods and ingredient valorization. That includes using pulses, agricultural byproducts, and protein to improve nutritional value while also supporting sustainability goals. Now on to single screw versus twin screw extruders. These two systems are very similar to extruders we've already discussed in class. Single screw extruders are typically used for simple, high throughput products and are generally less complex and lower in cost. Twin screw extruders are more expensive, but they offer greater versatility, better process control, and better performance when handling more difficult or formulation sensitive materials. So overall, single screw systems are preferred for simpler production, while twin screw systems are better for more complex food applications. In addition to the basic single and twin screw configurations, there are several different ways to classify food extrusion systems based on process conditions and product type. One category is hot extrusion. This is what people typically think of when they think of food extrusion. It's made to make products such as snacks, cereals, and pet foods, and uses heat and mechanical shear to cook and shape products. Cold extruders, by contrast, operate with less thermal input and are used for products like pasta, cookie dough, and some confectionery products where full cooking inside the extruder is not the primary goal. Another distinction is low moisture versus high moisture extrusion. Low moisture extruders are commonly used for puff snacks like breakfast cereals, while high moisture extruders are used for products like texturized vegetable protein and meat analogs. Co-rotating twin screw systems are also especially important for complex formulations because they provide strong mixing and greater process flexibility. And beyond those categories, there are many integrated or specialized machines that are dedicated around specific product requirements including pellet products, confectionery systems, and high-protein food applications. Building off of the last slide, we're going to talk about specialized food extrusion processes. In many cases, extrusion is not just a single machine, but part of a larger integrated production line. Some systems combine mixing, conveying, compression, cooking, and shaping all in one machine. Others use preconditioning before extrusion, drying after extrusion, or coating and seasoning steps downstream. There are specialized texturization systems used for meat analogs and high moisture protein products. So at an industrial scale, extrusion is often designed as a complete industrial process built around the needs of a specific product. Food extrusion remains highly relevant today because it continues to evolve with industry needs. One of the biggest innovation areas is high moisture extrusion for plant-based meat analogs. This has gained a lot of attention because it allows manufacturers to create more fibrous, meat-like structures from plant proteins, which has strong commercial value in the current market. Extrusion is also moving beyond traditional snacks and cereals into areas like personalized nutrition, targeted bioactive delivery, and functional foods. That means it is increasingly being used for not only convenience foods, but for more specialized nutritional applications. Another recent development is the integration with 3D food printing. This opens the door to customized structures, formulations, and product designs that may not be possible with conventional extrusion alone. The industry is also beginning to use AI and advanced process monitoring to improve real-time control, predictive analytics, and production efficiency. That is especially important in extrusion because product quality depends so heavily on precise control of operating conditions. Overall, extrusion remains highly relevant because it supports continuous processing, product innovation, and sustainability goals, including better use of plant proteins and agricultural byproducts. In conclusion, food extrusion is a highly versatile and efficient thermochemical processing method that plays a major role in food manufacturing. It combines material transport, heat transfer, compression, shear, and die shaping into one continuous process. As a result, it can produce a wide range of food products with high throughput and strong process flexibility. At the same time, the process depends heavily on machine design and careful control of variables such as moisture, temperature, screw speed, feed rate, and die geometry. Advances in high moisture systems, smart monitoring, and the integrated processing lines also show that extrusion is continuing to grow in importance. So even though extrusion is often discussed in the context of polymers, it is equally important in food systems and remains one of the most powerful manufacturing methods in the food industry today.